What if I told you that you could have infinite chocolate? One simple trick, a few precise cuts, and bam, you suddenly got an extra piece of chocolate. No extra ingredients, no magic, just pure geometry. You've probably seen this trick before, where you cut a chocolate bar in just the right way, and somehow magically you end up with an extra piece of chocolate without losing any of the original bar. But is this real? Let's find out. Today, we're putting the infinite chocolate bar trick to the test. Will we get endless chocolate? Or is it just going to be all an illusion? Let's find out. Okay, so let's go ahead and break it down step by step. So first, we get ourselves a standard chocolate bar. Sorry about the dirty cutting board. I just tried this with just a regular Hershey's bar and it didn't work out too well. So luckily, I found this Reese's peanut butter bar that will hopefully get better results with. So let's go ahead and we'll get our knife here. And we're gonna go ahead and make a diagonal cut, like so. And then we'll cut this way vertically. All right. And then we'll take a chunk off here at the top. This is our extra piece. And now we take these guys and just rearrange them. So this guy goes over here, and this piece goes over here. And voila. It looks like you still have the same amount of chocolate, even though you got one more extra one over here. So what happened? There is a phenomenon known as the infinite chocolate paradox. The paradox is simple. Take a bar of chocolate, cut diagonally, then vertically, remove a single piece, and then rearrange the remaining pieces back to the original bar shape. It looks like we're able to retain the original amount of chocolate with one extra piece to enjoy. Common sense tells us that the paradox is not true. Hence, it is an illusion, which you can see if you measure the length of the bar before and after. The remaining bar is shorter by the removed piece of chocolate. The animation itself demonstrating the paradox is misleading because the amount missing is sneakily added back into the animation. Obviously, you can't end up with more than what you started with. What if I told you that mathematically it actually is possible that you could have infinite chocolate? Enter the Banach-Tarski Paradox. This mathematical theorem proves that there is a way to take an object, break it up into a finite number of pieces, and put them back together in a way that will yield two identical copies of the original. This paradox is based on the weird nature of infinity. In this case, the weird nature is due to the measurable sets composed of immeasurable quantities. In other words, not all infinities are the same size. For example, the size of the countable numbers like 0, 1, 2, 3, 4, 5, 6 on to infinity is smaller than the infinity of the uncountable numbers. Now, what are uncountable numbers? Consider a set of numbers between 0 and 1. You can divide up the intervals between them into halves, or you can divide up into quarters, eighths, sixteenths, and so on and so forth, up to infinity. Think about it this way. Say you want to ask, what is a number after 0? Well, you could say 1, but you could also say 0.1, or you could say 0.001, or you could say 0.000000001, or you could even say 0.0000 a whole ton of zeros, 1. There's actually an infinite number of intervals between 0 and 1. And when you line up the whole numbers with the countables to the uncountables, The uncountable's infinity is inherently larger than the countable's infinity because between each whole number is an infinite number of intervals. Gerhard Cantor famously illustrated this idea with the diagonal argument. We can draw out a diagram attempting to find a one-to-one mapping between whole numbers and real numbers. First, we start with a list of real numbers between 0 and 1. This list of numbers can go on forever. Because there is no set starting point, literally any number can be the starting point. And so the numbers are enlisted in no particular order. Next, we pair each number to a whole number. If we could find a one-to-one mapping between the whole numbers and the real numbers, then the two sets would be the same size. However, it's guaranteed that you can generate a real number from the list that does not already exist in the list. How we can show this is by adding 1 to each digit diagonally down the list, subtracting 1 if the number is 9. That new number generated is guaranteed to not be in the list of real numbers, and so there can never be a one-to-one mapping between the whole numbers and the real numbers in this example, which means that the two sets are not the same size. Hey guys, real quick. Sorry about the bad handwriting. I probably should have done this on the computer. Here's the idea. We start with a sphere and pick a point on the sphere, and we tell the sphere to rotate either up, down, left or right by a distance of 2 pi r. Then we repeat the process, making sure to proceed in a unique direction. In other words, you can't double back. Because the rotation distance is irrational, you're never going to reach the same point. Now, remember the starting point? Well, because there are an infinite number of points on the surface, there are an infinite number of starting points. So, you can pick another starting point, repeat the rotation process, and generate a whole nother set of points around the sphere. And you can repeat this using different starting points an infinite number of times. Each set of points from the start to the end of the rotations can be separated out into its own sphere, which exactly matches the size and the density of the original sphere. And so that's why you could argue that infinite chocolate could be possible using mathematics. The infinite chocolate bar trick, it's just an illusion. It's a fun way to mess with your friends, but you're not going to get infinite chocolate out of it. But hey, if you want infinite chocolate, then just go buy yourself a candy bar.